So a quick introduction to Software Craftspeople community. So Software Craftspeople community is a not-for-profit organization. The aim is to connect people who share a passion for software craftsmanship. We host talks, roundtables, workshops to help everyone improve their craft. And throughout the year, we invite several experts to speak. Just a quick point about Incubite. So Incubite is the founder and sponsor of Software Craftspeople Community India, and Incubite focuses on delivering well-crafted software solutions. Um, so we have Jim today. Thanks a lot, Jim, for coming and giving this opportunity. Um, so Jim is a chief scientist at Neo4j, is a visiting professor at Newcastle University, and co-author of various books, including graph databases. And today's session is about distributed consensus. So over to you, Jim.
Thank you so much, and thanks everyone for giving up your evening to listen to me. My name's Jim. I am the chief scientist at Neo4j, and so I should be able to share my screen. Let me see. Hopefully, you folks can see my screen now, and it should definitely have the wrong event on it. Brilliant. So let me start by addressing that wrong event. So a few months ago, I was back in Bangalore after a very long time away from Bangalore. I used to live in Bangalore in a previous life. I went back to Bangalore for the Great International Developer Summit, and I gave a very short talk on distributed consensus. And on the basis of that talk, I've been invited to speak here at the Software Craftspeople event, and so I've had to change the talk a little bit. So now it's not the distributed consensus in 15 minutes, and I'm not going to constrain myself to just one protocol and to the kind of work that we do at Neo4j, but I'm going to give a slightly broader talk on distributed consensus in general. And because we've got a bit more time together, it gives us that space to think about consensus in a little bit more depth. Now, at its simplest, consensus is just agreement. And so we could boil it down to a problem that appears to be very simple. If I have two computers, can I make them agree on the same value, for example, a number? And there's a bit of a side story here. I told the audience at GIDS about this, and my background is I'm from a working class background. So all of my family and all of my ancestry are manual workers or clerical workers, and I was the first person in my ancestry to finish school, go to university, and certainly the first to get a PhD, which is not a brag. So forgive me, that's not the point of this story, but. One day, my mum asked me, with all of these qualifications and all this fancy computer stuff, she actually asked me, what do I do in my job with all of these computers? And I said to her, well, Mum, all I have to do is make two computers agree on a number. And she said to me, like the number 6. I said, yeah, that's right. If one computer thinks of the number 6, then I make sure the other computer also thinks of the number 6. And despite all of my qualifications and the fact that I was the first person in our family to attend college and all of that stuff, and my mum has been tremendously proud of that, when I told her that story, she just somehow looked very disappointed. Oh, she said, you just make two computers agree on the number 6. And she was very perplexed by this. Like, how can someone with all this, all this expertise in computing have such a seemingly dull job? Well, actually, it's not dull. Right? The real world in practice is so much more complicated. But the real world is full of failures, transient and permanent failures. It's full of all kinds of different error conditions, faults, race conditions that actually make coordination and consensus quite a difficult problem. In fact, this isn't a solved problem. Remarkably, although I'm going to tell you about some of the things we can do today, it's not a solved problem in the general case. And lots of research is still going on into expanding the utility of consensus. But importantly, we can make consensus work well enough in some situations for it to be useful, which means that we can start to build compelling distributed systems with within certain limitations which are useful for us. And look, I'm not going to talk to you very much about the kind of art and craft of software, but I am going to speak at perhaps the next level out. So as a software craftsperson, we're going to kind of look one level out and think of this more as systems craftspeople in this case. So how do we make compelling systems that are both pragmatic, useful, and pleasurable to build and operate? So let's have a look at our agenda. It's a bit more expansive than the one that I would have shown to you had you been in the GIDS audience at Bangalore. So first I'm going to talk about graphs and graph databases because that's the world I live in. And in fact, databases are often good candidates for consensus algorithms because we need to replicate data between instances of a database, between servers, so that we can get scalability and so that we can get fault tolerance. And so a lot of the work I do, although it has general applicability to distributed systems, I always end up homing it in Neo4j, in the Neo4j graph database. And as it happens, that has some interesting side effects that we may or may not get to. But I will talk about the fact that programming is too easy. And I realize that that is rather a provocative thing to say to an audience of craftspeople. But programming is too easy, and our hardware and our operating systems have made it too easy for us. But then I'll pose the question, programming is too easy. Surely distributed programming must be easy as well then. We'll see about that, because then we're going to talk about LP, Fisher, Lynch, and Pattison. Many of you in the audience may have heard of CAP, the CAP theorem, CAP theorem. And that was very popular maybe a decade ago when the NoSQL databases were gaining a lot of interest from our community. FLP is an older magic. It's a more fundamental discovery in computer science, which basically tells us computers don't work, so we shouldn't even try, which again is not a very strong platform for trying to convince you of the utility of distributed consensus. And then as we work through some of these protocols and approaches, I hope to be able to show you a way that we can both improve coordination for consensus algorithms and make coordination at the heart of consensus algorithms a lot more scalable before looking at some of the things that we might do in the future. Then we'll end and I'll take questions. But let me introduce you initially to my world. So you are all cordially invited the next time you're in London to come and get a cup of tea and some biscuits with me at the Neo4j office. So actually today I'm not in the office, I'm at home because I wanted some peace and quiet to deliver this talk. But usually you will find me here. And those of you that have been to London, you'll kind of recognize this. This is the London Underground system, or the Tube, as we call it. And there's a couple of interesting stations I want to draw your attention to. The one in the bottom left of the screen, that's Heathrow, which is connected via the Elizabeth line. And actually, this is an old tube map. So here, I think I've only got the Piccadilly line. Sorry, stale data. It's also connected by an overland train that goes to Paddington. And the other thing that I've circled is a station called Southwark, written Southwark, just to annoy the Americans when they come as tourists. But Southwark is the tube station just next door to Neo4j's offices. And if I said to you, hey, look, when you land at Heathrow, just hop on the tube and come to our office and I'll make you a cup of tea, you already have an idea how this works, right? You know the rules. You're not allowed to take a taxi, by the way. In fact, taking a taxi in London is crazy. It'll take you 3 times longer. But you know the rules that you're allowed to go from dot to dot on this diagram, providing the dots have a line between them. And that's actually a graph. So one of the paths that you might choose to take through the graph would be this one, right? So you could go up to the northwest of London, past Wembley Station, and then circle back through the city and then come south to Southwark. And that is a legal path through this network. But you already get the sense that there is a better way, right? That feels kind of a long way around. And in fact, there is a better way. And having done this journey, many times, the actual shortest path is probably here, which is Piccadilly to Green Park. Change at Green Park, and by the way, Green Park has a very innocuous name, but it's actually where Buckingham Palace is. So it's King Charles's tube station. Change at Green Park, and then hop on the Jubilee line, named after his mother's Jubilee in '77, and come down to Southwark. And that's actually the shortest path through this graph. Now, why am I telling you about this? Why am I trying to teach you about the London Underground network? Of course, I'm not. What I'm showing you here is a very everyday example of how graphs work. The stations in this diagram, they're nodes, and the lines between them, they're relationships or edges in a graph. And in fact, it goes without saying that graphs are actually highly intuitive, they're highly flexible, and they're highly explainable. So without even, perhaps you haven't even been to London, but you already know how to use this graph to help you to achieve some informational goal, in this case, to take a fast route from the airport to the office. And this is the world I live in. I live in this world of what's called labeled property graph model. And this is the data model that Neo4j has. And so we have nodes, and nodes typically represent entities. And those entities can be labeled with tags. This is a person, this is a product, this is a vehicle, this is a train, and so on. And you can put properties on them, effectively entity data on those nodes. And they're connected. The associativity in the problem is described using relationships. And relationships are always directed. They start at one node and end at another, or loop back to self. So they have a start, a head and a tail. And those relationships always have a type on them. It could be bought or father of, or that kind of thing. And they have you can put optional properties on them. For example, in the train example, you might put travel time on each segment of the track, and then be able to sum along the path to find out how many minutes it will take to get from one place to another. And this is a really simple model. And allow me to tell you why. Because when you were at college doing your computer science degrees, as some of you no doubtedly did, you read this book, the Al-Mazri Navathi book, which is brilliant. Absolutely stunning book, but it's well over 1,000 pages long to describe all of the ins and outs of the relational database model, a very popular model from the 20th century. Whereas actually to describe the graph model, I just need one, albeit widescreen slide. If I'm perhaps more honest, you can read something like this book, which is the Building Knowledge Graphs book, which is less than 300 pages. And if you're interested, that is freely downloadable from neo4j.com. Now, why do I say all of this thing? As I said, I work at Neo4j, and a lot of the technology that I develop around consensus goes into Neo4j. But ultimately, I build this so that people who use Neo4j have a nice experience. So in this case, because of all the work that goes on in the engine of Neo4j, when you're building data-intensive systems, applications, and systems that use data, you get to build it with a language that is that goes with the grain, with respect to your app. So here is what's called a Cypher query. Cypher is Neo4j's query language. It's now been standardized as ISO GQL, which was by the same committee that standardized ISO SQL. So that's nice. But here what we're saying is, hey, database, please find me, that's match, a node, that's the round brackets, which has the label customer. And then find me outgoing relationships labeled friend at depth 1 or depth 2, and that could be depth n or depth infinity, to another customer. And I'm going to give that customer the variable name friend. And where the original customer and the friend aren't the same, because a friend of friend could be yourself, tell me about those friends. And in fact, then find me where those friends bought bought a basket that had some product in it. That's what those arrows are representing. Return me the path, the product, ordered by count of product, and in a descending fashion, and limit to the top 5. So this is telling me how to find in a database all the things that my social network has bought, and tell me the most popular of them, and give me the top 5 back ordered. Isn't that nice? In fact, it is. But these relationships are interesting, right? They are real. They are materialized. They're not like joins in SQL. Joins at SQL are computed at runtime. In fact, that's one of the reasons that SQL-oriented databases don't work well for graphs, because we traverse these relationships all the time. But imagine having these relationships, for example, spread across machines. If I've got a sharded version of a graph database, and a relationship starts on one shard and ends in another, well, you can see it could be problematic there, because if one transaction, if you don't have any coordination, one transaction could be, for example, updating that relationship on the right-hand shard, while another is deleting it on the left-hand shard. And then you have to ask the question, which of those would be dominant? would the relationship in a minute's time, would the relationship be deleted or will it be updated? And the answer is, I don't know. And we've seen systems like this, systems like TitanDB and Janus Graph, when they run on top of Cassandra, they don't have this. They just allow natural arrival order to determine which write is dominant, and it can lead to corruption because in one shard, very well, the relationship could be deleted, and on another shard, it could be updated. So now, whether or not you see that relationship is non-deterministic because it depends on which shard your query starts. And of course, in a database, that's terrible, right? Because databases are this bastion of correctness. So, for example, if I follow you on Twitter, you should know that you are followed by me, irrespective of where the records representing you and I physically live. And this is something called reciprocal consistency. It was a paper the term originated with an Paul Esselchelvan paper in 2018 and followed on by Jack Wardby in 2020 in his PhD thesis. And the idea here is that if I follow you, you know that you are followed by me. If that relationship gets deleted, both sides know I no longer follow you and you know you are no longer followed by me, and the database remains deterministic. And that brings me to my next theme. Sorry to say to all you lovely craftspeople, but I'm going to tell you just how easy your day job is. Now, you know how lovely graphs are. They're amazing, and I love that. But they're not really the topic of this talk. In fact, how easy your day job is the topic of this talk. So I'm making friends already, I get the sense. So let's have a look at some programming. This is a fake language. It looks a little bit Java-ish, right? So int I equals 10, I equals 11, print I, and I get 11, right? Awesome. No worries there. That all seems perfectly reasonable, except, wait, what? Ha. Well, what? Hey, hang on a minute. How can that be? How can it now be, if I run it again, it now prints 10. Or if I run it again with a thread.sleep in it, it now prints 11. Wait a minute. And then, oh, no, it prints 10. Well, wouldn't this simply be incredibly frustrating if that's how your software behaved, right? It would just be, it would be impractical. But the funny thing is, your hardware does behave like this, even on a single computer, right? We have this myth that single computers are sequential, and they're not. Modern computers are amazing. They're doing all kinds of crazy stuff in parallel. They're doing all kinds of branch prediction stuff. They're doing all kinds of speculative execution. Your program runs out of order all the time, but there are these magic things called memory barriers which help to prevent these race conditions and make it look like our programs are running in lexical order. Right? It means our programs, our assignment, the updates to state in our Java programs, our Python programs work as you'd expect lexically. Later updates overwrite earlier ones. So in reality, what happens is I first set int I to 10, and there's a memory barrier that enforces that all cores can now see that memory location holds the value 10. I set it to 11, and again, a protocol kicks in, a memory barrier kicks in, so that all cores, even irrespective of where ultimately that memory location is cached, all cores now see at some expense that I is now 11. And so when I print I out, it is 11. This means our programs work as expected, and you as craftspeople can get on with the right part of your job, which is thinking about the elegant design of software systems. But there aren't any memory barriers in distributed systems. And if we implemented a memory barrier like this, I simply don't think it would work. It'd be far too slow to be practical. If you think about the kind of, what is it? The last time I checked, like something insane, like 80 gigabit bandwidth between L2 cache on a modern computer. We simply don't have that kind of protocol throughput in a distributed system, particularly once we leave the data center. So instead, we have a bunch of craziness. So I guess since you came to this talk, you quite like distributed systems. I'm going to try and put you off because distributed systems are cool, but they're also kind of insane. Because single-threaded programming on a single atomically failing computer is easy, right? The electronics does so much work for us. The electronics and the OS do so much work for us. So in theory, since it's the same electronics, it should be just as easy to build a distributed system. So let's see an example of an app. Now, we've all seen, a screen like this on a phone, on a what now looks like a very ancient phone with an actual tactile button. Crazy. So you're using some app, you've made some purchases, or you're trying to make some purchases, but you don't yet have an account. And you can either continue as guest, but in this case, you need to log in to continue your purchase. Well, I don't have a login, so I'm going to hit register. I'm going to create a very a personalized username here, and I'm going to write a password and hit create account. So far, so good, right? Now I'm going to log in to continue my purchase. I've just created that username and password, so I'm going to go ahead and type those in, and then I'm going to hit the login button, and wait, what? Account not found? That doesn't make any sense. How does that make any sense? I've just literally created a username and password. You kind of saw me type that in. What's even worse though, check this out. If I'd done this, thread.sleep 2000, the ultimate debugging tool for threaded and distributed systems. If I'd done that, typed in my username and password, now I get login successful. And in many ways, that's even worse, right? Because it's non-deterministic. Thread.sleep is not the answer to any of these things, right? It's non-deterministic. Do I thread.sleep 2000, 3000, 2001? And the answer is you don't know. And so this is insane. The equivalent of memory barriers in a distributed system is slow, it's hard to build, hard to maintain. And you can choose not to be bothered about any of this. And that even has a cool name in modern computer systems. We call that eventual consistency. And you will be told, by its proponents, well, the world is eventually consistent anyway. Well, that's not strictly true, because the world always has these informal protocols at the last possible moment that make sure things happen, or it has disastrous consequences. We don't let trains run uncoordinated and just hope that they go through points and merging in tracks safely. We actually, at the last responsible moment, will stop one train, we'll let another through, and so on. So the world really isn't eventually consistent, at least not the human world, or at least not a safe and pleasant version of the human world. So we need to make this eventual consistency stuff, for the most part, go away. Now, I'm not saying that the NoSQL databases got it wrong and eventual consistency is a bad, do not use it. But you can only use it in certain situations where there's going to be no contention between your values, right? If the value of A depends on B, you can't trust that to eventual consistency, because you need B to be consistent with respect to A, the reciprocal consistency stuff that Essel Chalvin wrote about in 18. And let me teach you about something called then FLP. You need to meet these folks if you're going to do distributed systems. And these folks, this is Michael Fisher, Nancy Lynch, who's quite famous, of course, and Michael Patterson. And a long time ago, they wrote this very fancy titled paper, The Impossibility of Distributed Consensus with One Faulty Process. And it's a very fundamental paper that amazingly not too many folks in our industry know about. It's older than the CAP theorem, which a lot of people do know, but I think it's more important. And this paper comes from 1985, right? So, at this point, I'm still at primary school. That's how well this paper has stood the test of time. And what they basically say is that if you have a faulty process, in the general case, distributed systems don't work, right? In the general case, distributed systems just won't work at all. So why would you even try? But in practice, things don't go catastrophically wrong all that often. So there's often a useful window of time where we can get things to work, where we can get useful reliability or availability out of our systems. But that's an important point in itself. I think one of the things that FLP also tells us is that you have to make a design trade-off between reliability and availability. And that's a hard trade-off, right? Because in my computer systems, certainly I want both of those. I'm pretty sure if you ask the question to your business stakeholders, they'd want them as well. Don't worry, these things are pathological choices, which means typically you can have reliability and availability. Reliability meaning that I will always give you the correct answer, and availability meaning I will always answer. In pathological cases, though, you are forced to make a choice. Will I be reliable? So I'll either give the correct answer. If I can't give a correct answer, I will not answer. Or availability, where I will always give an answer, even if I sometimes give the incorrect answer. And that's what happens in these pathological cases, particularly where failures occur. Now, in practice, you've got to, if you're doing a consensus algorithm, systems that require coordination will block for some failures, right? They will not give an answer because they would prefer to not give an answer than give an incorrect answer. But they will always pay the costs of coordinating, right? So consensus requires a coordination algorithm which makes sure all computers agree on the same value. Systems that don't use coordination, these eventually consistent systems, will be wrong in some cases. Whether that's a failure or a non-failure case, it doesn't matter because they give no recency or consistency guarantees. So you're always going to get some stale data from those folks. So what do we do when we're building Neo4j? Well, very much the version of Neo4j you can use today walks through the damned if you do doorway. So the version of Neo4j today uses a coordination protocol to safely commit transactions across multiple cooperating servers. So your transactions, your data as users is multiply redundant. So if I look at server A or server K, they all have the same transaction data on them. The graph that we store of your business domain is identical across them. And we use Raft as our consensus protocol. Now, Raft is cool. Most of the time when you talk to distributed systems people, they seem very smart. Not me, but the other distributed systems people. They seem really smart, and they talk to you about all kinds of Byzantine fault tolerance and contention and blah 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 and all these clever things. And it can be intimidating and baffling. And one of the bad things about distributed systems is that they're intimidating and baffling and complicated. And complexity is where subtle bugs hide. And subtle bugs in distributed systems often manifest themselves in non-intuitive places. So actually, things like Paxos, which is a consensus protocol that Neo4j used to use many years ago. At the time, we had about 20 engineers at Neo4j when we were a small startup, and we had greater than 20 opinions on how it works because that is a complicated protocol. With Raft, Ongaro and Oosterhout went the other way, and they said, look, can we make some simplifying assumptions so that the protocol itself is very simple? And if we have a simple protocol, even though it may not be the most optimal, if we have a simple protocol, there are fewer places for complicated bugs to hide. And so they designed Raft to be humane. It's a good thing. And in fact, Raft, as the name it suggests, is a pun. It's just a way of tying logs together. And logs are the data structure that underpins the database. It's where you write all of your user data. And the way it works is shown in this cartoon. So you have a bunch of servers, 5 in this case, but could be any number. And they have an election, and one of the servers becomes leader. And S3 is leader at the moment. And what the job of the leader is to impose an ordering on the transactions that the users are giving it. So the leader will send out, hey, we'll receive updates, inserts in SQL World or merges in Cypher, and it will then send out those transaction records, those transaction log entries to all the other servers and say, hey, could you guys append these into your log? And if it gets enough answers back, and enough in this case is a simple majority, so in the screen you're seeing that'll be 3 out of 5. If it gets enough back, it'll say, okay, cool, enough people agree now, so we will commit those entries, and they will be committed into the log. They will be immutable, and it will broadcast that out to the rest of the network. If the leader fails, well, the remaining machines have an election, and they also use the same mechanism of appending and committing to decide on who is the new leader. And so you've got this really nice property that both the user's data and the topology data of the cluster are all in the same log. So you've got the whole history of the distributed system in one place. And it also means that if your leader fails, you can seamlessly fail over to another machine in the cluster and keep running your system. In our case, keep running Neo4j, even if one of the machines fails, or in this case, even if 2 of the machines fail. So Raft is a protocol that keeps logs tied together. It's a pun. By the way, I didn't notice that was a pun until about 3 years after I'd started building Raft, even though the Raft team had little stickers with literally a raft on them. They contain entries for both the user data and the cluster membership. And like everything in Raft, Ongaro and Oosterhout chose the simplest possible thing. If a simple majority agree to something, it's considered committed. By the way, there are other systems. If you're interested in the work of Heidi Howard, for example, at Microsoft Research, she's done a bunch of really cool work on agreement with a minority of participants. But RAF takes the simple approach. So the simpler thing is, if the majority agree, we know the log is correct so far, and we can inductively continue. Anything that's applied is at risk, waiting for a majority to confirm it. But once something's committed, it's in the log forever. So we have this kind of motion where we have logs that are have agreement in enough of a majority, so enough members, a majority, to have the data applied. And this is perfectly fine here. You'll see that not everything across these machines is identical, but they're identical up to 10. And the top 3 machines are identical at index 11. And they will, I assume, become identical at 12 and 13. But because we have a majority of identical entries in 11, we know that the cluster will eventually make index 11 green and apply that additional node into the graph. And it's fine, actually, that all cluster members are slightly ahead or behind each other. It's a bit weird because Raft is a strong consistency protocol, right? When you run Raft, you're getting a strongly consistent outcome. But this is normal behavior. The speed of light is finite, right? So Raft, under a steady state, will give you a majority of immediately give you a majority of entries that are committed, but everyone else in the cluster will soon enough catch up with that and have the same log. But of course, there's always a race condition. The speed of light is funny. Network speeds are funny. Sometimes you can thread a request in that may not necessarily give you the answer you suspect. So let's take a look. So again, we're going to do that create account thing, right? So you've just seen it in the eventually consistent case. Let's see what happens when we apply coordination. So we're going to do create account, which creates a user. It adds it appends an entry onto the log there, appends an entry onto the log there, and appends an entry onto the log. Oops, sorry, bad cartoon. Should have appended an entry onto the log in the middle one as well. So now we should be able to log in. So because we've got enough of a majority, we do the login, but then we get no account found. Again, what the heck is happening? That's really surprising because we've done all this work to get a consistent outcome. We've run a consensus protocol that ensures that all of these machines should have the same data on them. But for some reason, something happened where the machine I happened to read from, where my account was going to be validated, where I was going to authenticate, and it didn't have that data. And that's really frustrating. But it's because Raft wasn't designed for that. Raft was designed to get a simple majority of servers in your cluster to agree to a value, and then the others presumably catch up very rapidly. So at Neo4j, we added a layer on top of Raft called a bookmark. Terrible name because it's not a bookmark. It's really just a session token. And what we can do there is provide a causal barrier. So in this case, if we're going to interact with the database and we want to always see at least our own writes, then what we'll do is we'll obtain a bookmark, as you can see here in this final line of this code. From the session, we get a last bookmark and we remember it. And then we can use that bookmark. So here's how we'd obtain the bookmark. We can then use the bookmark. So when we're creating another transaction to actually use the username and password that we've just registered with the system, we can give it the bookmark, and we're effectively telling the system, hey, system, this is the last transaction that I saw, and I want you to run my next query only when you've processed that transaction at least. And so here you then have this lovely situation where you send your login over to the system. Perhaps the bottommost server hasn't yet processed your account's creation, but you'll be paused momentarily. That transaction that creates your account will run. Once it has run, your query is then released to do its run, so you will effectively log in without seeing this kind of account does not exist nonsense, which is lovely because now we've got a couple of cool things. One, we've got reliability. Right, and that's a hard thing in distributed system because things fail and you need redundancy. But two, the database acts like a variable, very, very similarly to how your variables behave in a programming language, greatly simplifying how you would build systems on top of it, right? So that's so cool. So leaders are great. So I like leaders because they centralize hard parts of the distributed system and allow us to do ordering. And ordering is important, right? Every machine has to agree A before B before C. If that diverges, you've got corruption. Leaders are fault tolerant, and they can move around the cluster as failures and recoveries happen. And every leader in Raft is guaranteed to have the same committed history as the current leader. So you can't lose data. Anything in Raft that's been committed is there. You can't lose it. But the one thing that Grumpy Cat is telling us is that the leader always coordinates all the followers. And what that means is that they're a bottleneck. So we get a lot of good things from these architectures. We get correctness, we can layer on causality, so they behave like variables, but we're running this machinery all the time, and sometimes we don't need to. So can we improve coordination? Can we walk through the door that says damned if you don't? Well, we know that correctness for graphs requires some kind of coordination. Otherwise, one transaction can be updating a relationship and one can be deleting it, and we don't know which ones win. But coordination is typically considered the enemy of scalability, right? This is why the NoSQL databases, things like the amazing Apache Cassandra, were considered to be so revolutionary because they were incredibly high performance. But in order to gain that performance, they let go of any consistency guarantees and they didn't do any coordination at all. So here's the Essel Chalvin paper that I mentioned earlier. And what he and Izzy Matrani and myself observed when we modeled this, so we built a simulation, we built a mathematical model of this, is that in order to preserve reciprocal consistency, so a relationship or edge that spans between shards, both servers must update their records in a way that is mutually respectful. So if we're deleting that relationship, both records that reference it on different shards must agree that it's deleted. And you can't have one agree that it's deleted and one that hasn't. And if you don't have reciprocal consistency, so for example, things like Janus graph on Cassandra, then very quickly, with no hardware faults, with no failures, you start just race conditions that are inherent in eventual consistent systems. You get corruption in your graph, and in the graph world, the corruption then spreads around the structure of the graph. And the estimate that we got from this research work was for any reasonable transaction or database of any reasonable size with any reasonable transaction volume, your database is useless. That is about 10 to 20% of it is just pure garbage within about 6 months. And I don't think your business stakeholders like that very much. So we need to do some more computer science. As you can see here, I'm trying for the Alan Turing look myself, but failing miserably. So we know that Heidi Howard says that that you don't need to have majority for consensus. When this is a really cool result, by the way. As part of her PhD, she's now, as I said, at Microsoft Research, doing very, very smart things. And so if you could make the consensus protocol cheaper by involving fewer machines, then it should be quicker, right? You should get higher throughput. And there are cool ways of doing that. Instead of just having a simple majority like Raft does, you could organize your consensus groups as trees or rows or other kind of structures. And you can get, during the happy path, you can indeed get greater throughput. But the trade-off here, and there's no such thing as a free lunch, the trade-off is that when machines fail, the recovery is much more intricate. In the Raft model, any machine failing and recovering is the same as any other. But in one of these kind of fancy consensus arrangements, different machines need to recover differently depending on where they are. Your mileage might vary, but Raft always picks simple. And I'm a huge fan of simple because complex is where the bugs hide, and bugs in distributed systems are subtle and devastating. Another way of doing this would be to avoid coordinating wherever possible. And this is a really cool idea. This was Peter Bayliss's work, and my old mentor Alan Fekete at University of Sydney, and their observation here was like, do you always need to coordinate? And they found that in TPCC, which is a popular relational database benchmark, you only actually need to invoke the coordination protocol 13% of the time in order to preserve correctness, which means that 87% of the time you don't need to go through this expensive path. But most databases either coordinate 100% of the time or 0% of the time. So you can see there's a middle ground here that these folks tried to reach, where you can say, look, for some things we need to coordinate, for some we don't. For those things that we do, we'll pay the cost, and for those things that we don't, we'll get a faster system. So there's a common theme here, though, right? And it's the coordinator. And the coordinator's job is to figure out who goes first. Is it, in this case, is it Rosa, then Carl, or Antonio? A before B before C. So having smaller quorums is useful. Having the coordinator do less work is useful. So that's a kind of cool idea. Well, the problem is there'd still be the coordinator, and that's problematic for scale. So how do we make coordination itself scalable? Well, we know a common theme in distributed systems. In order to make things scalable, we add more computers. But actually, just adding more computers to coordination it tends to be harder than you think. But there are a few ways we can start to think about this. Now, in the old days again, and it's quite fun, I'm showing you a lot of old papers here, but some of these things really have stood the test of time. There was this idea, which never really went anywhere, called chain replication protocols. And this was just a way of getting databases to make multiple copies of their data for fault tolerance reasons. And you can see the architecture here. It's pretty straightforward. You put updates to your database into the leftmost system, and they get propagated linked list style into through several more computers until they hit the tail. And it's a simple system. It has annoyances. If the machine in the middle of the chain dies, you have to kind of figure out how to repair the chain, and inserting computers into the chain is a pain and so on. But it's nice, right? It's got some really nice properties, like it scales reasonably well in terms of the number of replicas, and you're kind of guaranteed that you've got, provided you can maintain the chain, that you've got fault tolerance. Why am I telling you that? Well, we're not here to talk about replication. That's a fairly simple problem because you're making a carbon copy of each machine. But instead, chains can have other interesting properties. And one of the things that we noticed in our literature review was this, again, very unknown paper, but it's very impactful for us, that you can use chains to organize not just replication, but transactions. And the thing that sparked our interest was this idea of one copy, serializable ACID transactions with no spurious coordination. This is known as linear transactions. And these things, one copy and serializable and ACID and spurious coordination, these are proper serious database things, right? So serializable is a really strong guarantee that you understand the history of operations on a database. And no spurious coordination means that you don't do any work that you don't have to do. So you can take this replication idea and you can turn it into this transaction protocol idea. So you go from on the outward bound, you go across all the machines, telling them, hey, can you do this? Can you do this? Can you do this? And on the way back, you say, okay, commit, commit, commit. So this is nice, right? This is kind of analogous to a commit. And you might even say that. You might say, hey, Jim, this looks a lot like two-phase commit, but instead of having a coordinator, each machine is responsible for the next stop. And I think you're right. Right? I definitely think you're right. Same drawbacks as 2PC, and maybe it's actually even harder to reason about because there's no single coordinator. But bear with me for just one more second, just for a second before you tell me it's silly, because the genius comes here. We know that ordering things in a distributed system is hard. Total orderings, knowing the exact order of every transaction across the whole distributed system, is completely safe, but also completely impractical from a scalability point of view. Some partial orderings are safe, and they might also be practical. Now, with chains, what you can do is determine an ordering of two transactions, A before B or B before A, not but in some outside system like the coordinator, but in the system itself. And in fact, the genius of this paper is saying, look, If I've got two transactions that overlap on a server, it doesn't really matter whether it's A before B or B before A, as long as everybody else applies in the same order. So that particular server can decide on an ordering, it can flip a coin and decide on an ordering. And as long as when that server says A first, then B, any other servers that have A and B as a transaction on them must apply A first, then B. And so on the forward pass, you can now not just do the prepare part of a transaction, but you can also send some metadata with it that says, hey, look, on server 3, we had Rosa and Carl both issuing transactions there. And so server 3 can impose an ordering, right? Not the natural arrival ordering, can impose an ordering, a coin toss ordering. And in fact, if that server decides that it's Carl that finishes first, then it will say everyone that receives Carl and Rosa's transactions must apply Carl's first, then Rosa's. And so then on the way back, all of these machines get to apply the transaction in exactly the same order. But every machine in this cluster has the ability to make a local decision when it needs to. And when it doesn't need to, when the two transactions don't overlap, as in this screen, there is no reason to do the expensive coordination thing. Just apply the transactions. And so we're off to the races. And I think this is really underappreciated genius. The question, should Rosa go first or Carl, doesn't matter, provided that the order of application, as we call it, is consistent across all the servers. So you can do it with coin toss, you can do it with perceived arrival order, you can do it with first, in this case, first to change direction. And what this means is it's brilliant because we can have many coordinators and we only have to invoke the expensive thing when chains cross, when transactions contend with each other at a particular shard. And that allows us to do scale out while maintaining the kind of ACID semantics that we're used to from databases like Neo4j or Oracle or MongoDB and so on, which is very cool. But chains are unwieldy. What if we had a large system? Those chains can be very unwieldy, particularly if I've got replicas. You see here, I have a chain length of 9, where I've effectively got 3 shards, each with replica size 3. And that's kind of a pain. So what you can do instead is mix things like Raft or Paxos if you're a masochist, and use the chains to do the coordination between the shards, and then use something like Raft to simply replicate or carbon copy inside the shards. So the number of machines that you have to worry about for chains is much smaller. Now, don't get me wrong, once you get down into the weeds here, this introduces leader again with all of its jitter and so on. And we've seen that Chokler and Gottsman again back in 2018 have a fast path for Paxos which might beat this. But this allows us to do that marvelous thing where we don't coordinate where we don't have to. So I think where we're going, we don't need leaders. We can use things like these chain-based protocols for inter-shard coordination. We can use Raft to be able to replicate data across machines, so we've got fault tolerance and redundancy. But we don't have to use leaders. I mean, leaders are great, don't get me wrong. I love the fact that they solve the ordering problem in one place. I love the fact that Raft leaders can resurrect themselves on other servers, so the protocol's non-blocking. But much like Warp, I would love to have decentralized coordination, but I don't want its limitations. So one of the things that we're doing, there's loads more computer science to come here. One of the things that my team are doing at Neo4j is this idea of conjunction of majorities transactions. And it was theorized by Tobias Lindorker, who's now at Pinecone, and me some years ago. And the idea here is that each transaction carries some metadata with it. In fact, it carries a directed acyclic graph of all of its ancestors that it depends on. It's rather like a Git hash. It's like I depend, I was based on, my commit is based on this previous commit. And so we carry that list of ancestors. And when it lands on a shard can make a local decision and quickly reason about whether it can commit the transaction based on what the transaction has declared its version is versus the local history of that shard. And if I can get a majority within a shard to agree to commit that transaction, then that shard can commit. And if all shards involved in that transaction can manage to get that majority based on the transaction's metadata and the local state, then the whole thing can commit across shards. What's lovely about this is that every machine in the cluster can coordinate. yeah, when they need to, and they won't coordinate where they don't. And in fact, in the simplest case, you have a simple transaction within a shard, and you just need super lightweight coordination on that, just the metadata, and you only need to invoke the bigger, more expensive process where you've got heavyweight transactions that span the whole system. Gives you a strong guarantee, so you can do serializable. You can't do some things with this, so you can't do cardinality enforcement, but it is super cheap to process and it has low contention. And actually, part of my day job at the moment is building a prototype of this. So there's lots of interesting work to follow in this domain. So wrapping up, Raft is amazing, and I think for most distributed systems, if you're going to do consensus, Raft is the way forward. Certainly, these research prototypes are coming your way, but they're a few years out, and they need to be baked a bit more before you get your hands on them in business information systems. So Raft's great, it's safe, it's performant. There are very few places for bugs to hide. If you wrap it in a causal barrier, as Neo4j does, you can always read your own writes, even if you've deployed your system over a WAN. Zooming out, distributed systems are hard, and the research into them is ongoing. But one thing I would bring to your attention when you're building these systems, you're crafting these systems, is that the FLP work shows there are trade-offs, and those trade-offs are universal. In the pathological case, you'll always be forced to choose between correctness and unavailability. If you like what I've spoken about this evening, then let me draw your attention to this book, Patterns of Distributed Systems by Unmesh Joshi. It's a Martin Fowler book. It's really, really good. I was a reviewer for this book, and they quite kindly asked me to write the foreword for them, so I'm very familiar with it. Grab that book. It's a really nice way of thinking about distributed systems as a set of interacting Lego blocks. And on that note, I will pause and ask if you lovely folks have any questions that I might answer. I see chat. Let me just check. Okay. I see nothing in the chat. Does anyone want to unmic and ask me a really difficult question?
So not a question, just an observation. Like I'm also currently reading a book about this distributed. So basically the book name is Designing Data Intensive Application. And I think 80% of the book talks about distributed system and its fault. And there are a lot of things that this book talks about, even the physical vibration of the server that we don't think about.
Yeah.
And we only believe in the happy path. We think that, okay, this is how the code is going to flow. And that is how the normal software developers think. So reading that book actually provokes me. Don't create that complex architecture unless you are very much sure about what you are doing. Be happy with simple things.
I love that book. That's the Martin Kleppmann book, isn't it?
Yeah,
Look,
correct. Yeah.
Martin is a genius, right? And it's really interesting because he's written this book. It's a beautiful book. I love that book. There's a copy on a bookshelf behind me. It's great. He's so clever, and he writes this beautiful book about distributed systems. And you're right, one of the key warnings from someone who is basically a genius says, what I'm about to tell you is really cool, but if you can avoid it, please do. And I think that's one of the smartest things that geniuses tell you, right? There's a hard trade-off if you follow me, and if you can avoid following me, you'll be happier, which is a horrible thing as a distributed systems practitioner to have to say, but it's very true. So don't be prideful. I think when you're crafting, you take pride in your craft, obviously, but if you are too prideful, you want to build something that's, a monument when you really needed a tool, then you're going to get all of that bad stuff that Martin describes in his amazing book. Okay, good question. We're working with CRDTs. How does that fit with distributed consensus? Well, CRDTs were designed specifically to avoid consensus. So that's a wonderful question. Thank you for bringing it up. So a CRDT is a data structure, and the idea is that some data structures, like for example sets, they have this really nice aspect property that they are. Oh man, what's the scene? No, they are. I forgot my English. This is terrible, but you can effectively do the operations in any order. And if you then merge commutative, thank you. Finally, my brain remembered English. They have this commutative property where you can do the operations in any order, and then the set at the end looks like the set that you would have had if you had one of them. So what's nice about this is, like, if you have a set, but then actually the set diverges because you've got two computers and there's a network split between them. You can both happily write into those two computers. When the network split heals, you can bring the set back together and you can merge the data quite happily. That's awesome, and it works for some data structures. But imagine a graph, which is a thing I work on, and we get the same thing. So we get a split, and I've got two computers and they're both accepting writes. And on one computer, we delete the Jim node and we delete all of his relationships to his family. Oh, I feel horrible. But on this node, on this server, we add some more relationships. Maybe I get some more friends or some more family. And then when the network heals, we bring them together. What do I do? Because on this computer, Jim is dead and has no friends. And on this computer, Jim is alive and has even more friends. And the question is, which one is truthful? And the answer is, I don't know. So what the Shapiro paper tells us, and Shapiro was the guy that pioneered CRDTs, was like, you just impose rules. You just basically say, well, this computer's correct and this one's wrong. Or you say things like deletes have precedence over updates. And that's fine because it makes sure you can write a compelling computer science paper that is itself consistent. But in your business domain, how does he know that deletes have precedence over updates? In your business domain, updates of family members may have precedence, but deletes of pets may have higher precedence, and you just don't know. So basically, if you're going to use CRDTs, there are a small number of data structures for which it works, and you should think about that as being very similar to when I can use an eventually consistent database, because CRDTs are effectively eventually consistent data structures. Thank you for the question, though. That made me think.
Awesome. I think one more question, I think from Mansoor.
Okay, Mansoor, how is data security handled by Neo4j? So I'm not a security expert, but I'm gonna are we saying data in transit, or are we what element of security are you interested in? And I will try my best to answer.
Data at rest. Can data be encrypted?
Yeah, so that's something I don't know much about. I do know that Neo4j now allows you to do key management for data at rest, but I have no idea how it works, and I've never worked on that team. When I last committed code into the main Neo4j branch, all we had was data that was secure in transit, and we didn't didn't encrypt data at rest with your keys. Nowadays we do because of the cloud service and so on, but I don't know how it's done, I'm afraid.
All right, no issues.
Sorry about that. When Neo4j was small, I felt like I knew every single component in the whole system, but now there are like 300 engineers and they write more code than I can read.
Understandable.
Mansoor, just a note on that. If you drop me an email afterwards, I'm just jim@neo4j.com. I can always connect you to our security team who will be able to give you a full answer for that.
Sure. Thank you.
Cool. I think we don't have any more questions. Thanks a lot, Jim, for joining us today. And thank you all the participants who took out their time. If you missed anything, the recording will be available on our YouTube channel. We share the link on social media. And let me just quickly share the link. Additionally, we have the next session coming from Sven Peters, which is regarding developer joy, how great teams get things done. So don't miss this session.
Thank you so much, Jim. We really enjoyed it.
Thank you very much. Thanks, folks. Have a great evening.